Welcome back to Chem 4300. In this video, we're going to be covering Chapter 5, which looks at the classical physics of vibrational motion as applied to molecules. Now, to do a proper treatment, we're going to have to use quantum mechanics, and we'll do that later in the course. But the idea of this chapter is simply to introduce you to the classical physics concepts of vibration, and then we'll use those, pick up from there when we go to quantum mechanics later. So let's start with the simple harmonic oscillator, which is probably the simplest case you can imagine mathematically. The idea then is we're going to have a mass of m here that's going to be attached to a spring that's going to be fixed on the other side. We're going to define a coordinate system, x here, that has a value of x equals 0 when the mass is in its equilibrium position. And as we displace this mass, as we sort of pull it out, then we're going to be pulling it towards positive x values, and as it sort of gets pulled back by the spring, then it will go past its equilibrium position into negative values and then be pushed back out as it oscillates here. We'll assume that there's no friction, and we're going to assume that we can just worry about the mass of the ball. We don't have to worry about the mass of the spring. So as I said, we're going to take this ball and we're going to pull it and let go, and we're going to look at its position as a function of time. And we know what that's going to look like. We know that if you pull the ball out to some initial position, there'll be some initial amplitude, it will oscillate back and forth. Now, there's no friction, so it'll just continue to oscillate on and on forever since there's no friction. Now, in this plot here, then we would define the cycle, this capital T, as the time between the crest or troughs there. So what we want to do is we want to get the equations of motions to describe this position as a function of time, and also the velocity as a function of time. So we'll start with what is the force that's acting on the mass. And in this case, it's the force due to the spring. And we can write that force as in this form here. So the force from the spring is going to be minus some force constant times the position of the mass. So taking that force from the spring and using Newton's second law, well, mass times acceleration is equal to our force, then we can rearrange this. This is the second derivative of the position, which gives us this differential equation here. Now, for a differential equation like this, we simply propose a solution, substitute it in, see if it satisfies this equation, and then we have a solution. So we're going to take a solution. We know it's oscillatory. We already have a good insight that it's going to be oscillatory, so we'll just propose a solution like this, and then we'll take its first derivative and its second derivative. We'll substitute the second derivative into there, the function into there, and we will get this result here. So this is the equation we need to make sure has a proper solution. And you can see right away there's an obvious solution here. I'll go to the next slide, which is that if Kf, the force constant, is equal to mass times this acceleration, this angular velocity squared, then we have a solution where this is true at all times. So this velocity here, this frequency, is what's called the natural oscillation frequency for the harmonic oscillator. And if we want to calculate the velocity as a function of time, then we simply take the derivative of our solution, which now becomes this. And if we take our initial conditions, which is initially we pulled the mass out to a particular position, we'll call x naught, and initially at time 0, the ball was not moving at all, so it had 0 velocity, so that means that x dot has to be equal to 0. We can take these initial conditions and we can use them to find that phi has to be equal to 0, and a is defined as x naught, and so we get this solution here for the position and velocity as a function of time. So there we've solved the differential equation, and we have the solutions. Okay, let's move on now. Let's consider the energy of this simple harmonic oscillator. If I write out the energy, I know it's going to be the sum of the kinetic and potential energy. So we'll write down that the kinetic energy is 1/2 mv squared, or if you like, the momentum squared divided by 2 times the mass. The potential energy for the spring we'll get by integrating the work. So we can integrate the work from 0 out to some position, which is our force that's being applied, which is kf times x. We do that integral, we end up with 1/2 kf x squared. So that's the potential energy which you get from integrating the work from 0 to x. Now, this is for extending the spring. If we wanted to compress the spring, we just change the limits from -x to 0, but you'll find that you'll get exactly the same result. So for compression or extension, you get the same result for the potential energy function. And this function here is just simply a parabola, right? It's a parabola with a minimum at x equals 0. So given that, then, we can write down that the total energy is 1/2 mv squared, plus now our potential energy, 1/2 kf x squared, or if you want to write it in terms of momentum, this way here. And if we plotted, then, the total energy, the potential energy, and the kinetic energy, you can see that, of course, the total energy is constant. The potential energy starts out as a maximum and then goes down and oscillates down to 0 when you are at equilibrium position. And you see it oscillates like this. The kinetic energy is out of phase, and it starts out with 0 kinetic energy because initially you're not moving, and then it goes up and down with the 180 degrees out of phase with the potential energy. But the sum of those two guys is always constant, which is the total energy. Now, if I take that, those equations that I have for the velocity and the position that we solved earlier, we can plug them into our energy expression. So if you remember those expressions, here's the velocity expression, here is the position expression. So if I take these expressions and I do a little substitution here, so one thing I can do is I remember I've already solved for this kf and its mass times the velocity, angular velocity squared. So if I plug that into there, then this expression becomes this expression here. I can pull out this common term out here, and now you see I just, from a simple trig identity, this guy becomes 1, and so we have the total energy is equal to this expression, where it's simply related to the mass, the frequency squared, and then the position, initial position squared. So that initial position then is really defines how much total energy that you put into this harmonic oscillator. So I can redefine the problem then as the initial position, solving this in terms of the energy and the mass and the natural resonance frequency for this spring. So I can take the equation where this was my x naught here, and I can substitute this guy in, and now I have an expression where I have the position as a function of time written in terms of the total energy. Okay, and that will be useful later on in the course. So next, let's look at something that may seem a little weird, but it will be useful later in the course, which is what is the probability distribution for the harmonic oscillators? In other words, at any moment, if you looked at the harmonic oscillator, you would see the ball in one of these various positions. So if you looked at those positions and you made a histogram of where it was over many sort of oscillations, you would get a probability distribution. So let's see if we can derive that probability distribution. So we'll start by just scaling by the initial amplitude. So we have a function we'll call y, which is just the oscillation, cosine omega naught t. So that's a very simple function. And what we want to get is the probability that we have the ball at a particular scale position y, which y is now going to fall between -1 and 1. So the way we're going to do that is we're going to say that the probability, so the probability density function times some interval, is going to be proportional to the time spent in that interval. So how much time it spends in a given interval is proportional to, the probability of finding an interval is proportional to the time it spends in that interval. And so we'll have a proportionality constant b, and then dt is the time interval that it spends in that position interval. So what I'm going to do is do a little trick here. I'm just going to do dy over dy, which is just 1, and then I'm going to rearrange this. So this is pull the dt over and pull one of the dy's back over here. So now I have dy times dt over dy, and this we recognize as just the velocity. So I'm going to 1 over the velocity. So that's now going to become b over v dot, and then that's times dy. All right. So now if I use my definition for the velocity, my scale velocity, which is this now. Once I use my expressions from before, I can take my definition for the probability density function in this guy, substitute it in, and this is what I get. Now I do a little rearranging here. I'm going to take sine omega naught t, I'm going to replace it with 1 minus cosine squared omega naught t, then square root of that, all that in parentheses here. And then I'm going to recognize this guy as just my y function squared, and that goes in there, and that's my probability distribution up to this point. All right? So that was the derivation of the probability of the mass being in any position y. So this is the probability density function. So given this probability density function, we still have to normalize it, but now we know how to do that. So if you normalize this function, integrate it between -1 and 1, and then normalize, you'll get this as the final distribution function that's normalized. So what this looks like, if you plot it out, is over here. So here's our probability function, and it goes from -1 to 1, and this is what the probability looks like. So it's a pretty odd looking probability, but it makes perfect sense. You know that when you pull the ball out, initially, before you let go, it has 0 velocity. So it's going to be spending a lot of time out here where it's moving slow. But then as it starts to go back, when it passes through the equilibrium position, that's when it's going to have the maximum kinetic energy. That's when it's going to have the highest velocity. That's when it's going to spend the least amount of time. But then as it goes past the equilibrium position, over here it starts compressing the spring. Then it will slow down. And as it slows down, it will reach the maximum excursion on the other side, where it stops and starts changing direction. And in that point, then it's also going to spend more time because it's moving so much more slowly. So you see this distribution then sort of makes sense that at the two ends, the turning points, these are what we call the turning points for the motion, it spends the maximum amount of time, and it spends the minimum amount of time here at this equilibrium position. So this is a very useful result because we'll come back to this when we look at the quantum treatment of the harmonic oscillator. We want to know how a classical harmonic oscillator behaves, and we just derived what its probability distribution looks like. Okay, next what we're going to do is look at a diatomic molecule as a harmonic oscillator. So we're going to take a model that is now 2 masses, so mass 1 and mass 2, connected by some spring, and they're in some position R1 and R2, and we're going to look at the potential between these guys. Now the actual potential between these looks more like this solid line here, and this is actually a plot of something called the Morse potential, which is a good potential modeling a diatomic molecule's vibration. And you can see this sort of is what you might expect. So you can see that there's a minimum here where the potential is minimum, where the restoring force is 0. So there's no force acting on the masses when we're down here at the minimum. But if we move to either side, then you'll see there'll be a restoring force. So if you're over here and then you've stretched the bond, then there'll be a restoring force pushing you back to equilibrium. If you're on the other side and you've compressed the bond, then there's a restoring force pushing you back here to the equilibrium side. Now, in this Morse potential, the solid line here, you can see that it goes up very steeply as you try to compress the two atoms together. So as they come closer and closer, the potential rises up, and so there's a very strong force, restoring force pushing it back to the equilibrium position. But you also see that in this Morse potential, there's an asymmetry here. When you start stretching it, at some point, there's a restoring force always trying to push you back to equilibrium, but at some point, that restoring force goes to 0. So the slope of the potential goes to 0, and when you have these two atoms infinitely far apart, then there's no force acting on the molecule because the potential, remember, is flat here, and the force, restoring force, is the derivative of the potential, which is 0 when you're out here. So at r equals infinity, there's no attractive forces. Now what we're going to do is we're going to say that if we're in this region here where we're just vibrating just very slightly, that in this region it sort of looks like the parabola that we had for the potential energy of the harmonic oscillator. So we know that it's not completely true, but it's pretty true, when you're close to that equilibrium. So what we're going to do is try to run with this idea that we're kind of like a harmonic oscillator in these small vibration limits. We're going to do a Taylor series expansion of the potential. So we're going to take the potential energy function and we're going to expand it about the equilibrium position. And if you remember your Taylor series expansion, if you don't, make sure you go back and review this. Then it's going to be the first derivative with respect to x times the deviation from that point about what you're expanding, so r minus the equilibrium position here. And then the next term is 1 over 2 factorial, and then the second derivative with respect to r times the square of the deviation from this equilibrium position. And then the third term is 1 over 3 factorial, and then the third derivative times the cube of the deviation from the equilibrium position. And you can now generalize this 1 over 4 factorial and the fourth derivative and the deviation to the fourth power and so on. So this is a Taylor series expansion. So what we're hoping then is that for small vibrations, we can use this expansion to take something like the Morse potential and get a simpler version when we're close to equilibrium and just vibrating very, very small amplitudes. So this VE, as I said, is the potential energy at the equilibrium bond distance. The first order term, which is the first derivative of the potential evaluated at the equilibrium position, well, that actually is 0. I'll just go back to the previous slide right here. If you evaluated the potential here, then you can see the potential the derivative here has a slope of 0, so there's no force at that point. So that means that this derivative has got to be 0. So with this expanded about the equilibrium point. So we'll be able to eliminate the first term because it's 0, and that leaves this as the next term. And this term here will follow that one. So what we're going to do is define two constants. We're going to define our kappa f, which we had earlier, is going to be defined as simply this second derivative of the potential. And now we'll define a new constant here we'll call gamma f, which is going to be the third derivative of the potential. And now we can take this expansion and rewrite it out like this. And so there'll be higher order terms, but the idea is when you do a Taylor series expansion is that you should be good if you're looking at just the first couple terms, as long as you, in this case, you don't have very large vibrations. So we're gonna drop, in this case, we're gonna continue to be approximate, and we're going to even ignore the third order term, and you can see that when you ignore the third order term, you have something that looks like a simple harmonic oscillator. But if we go to larger displacements, then we're going to have to include this anharmicity term here. All right, so now let's go back to the diatomic molecule. So we're going to look at this completely from a harmonic oscillator point of view. So the harmonic oscillator approximation, go back, is simply just stopping right here. That's the harmonic oscillator approximation. But if you want to account for anharmicity, you could do that by including a higher order term. And there's no reason why you simply can't just take the analytical expression for the Morse potential and use that, but that's going to be a lot more challenging in terms of the math. So we're just going to try to look at this from the as simple point of view as possible. So let's look at the diatomic molecule. And in this case, then we're going to be looking at the restoring force and on each one of these guys. So here's mass 1 and mass 2. For mass 1, the restoring force will be minus kf. And then it's going to be the difference between R1 and R2 plus RE. This is going to be the term that multiplies times this to tell us how big that force is. Similarly over here, for this guy, it's going to be R2 minus R1 minus RE, and this will give us the restoring force acting on that guy. So what we're going to do is we're going to write down with Newton's second law, we're going to get two equations of motion here with these, using these two forces, and these are coupled differential equations, and we need to solve them, and the way to solve them is to find a way to decouple them. And an easy way to decouple them is to transform this problem into a center of mass frame. So we define the total mass as m1 plus m2, and we define the center of mass as capital R, as we learned earlier in the class. So if you make a transformation into this frame where we're into the center of mass frame, then you'll find that these two differential equations get turned into these two differential equations, where now we see that the center of mass, so the total mass, and then the rate of change of the center mass, the acceleration of center mass is equal to 0, and then this guy, which is what's called the reduced mass, which is defined as 1 over mu is equal to 1 over m1 plus m1 over m2, is in a differential equation that looks exactly like the simple harmonic oscillator differential equation. So instead of mass, we have reduced mass times the acceleration is equal to minus kf times delta r, where delta r now is defined as this difference here. Okay, so now we've taken this problem, the diatomic molecule, and with its two coupled differential equations, and we now have gotten ourselves down to a simple harmonic oscillator differential equation to solve. So let's look at this equation here. We know the solution. It's all going to look like what we had before, so we're going to write delta r is equal to delta r naught, so the initial displacement, and then cosine omega naught t, where omega naught is the oscillating frequency. It's kf over the reduced mass this time, square root of all that. Now in spectroscopy, we can actually measure the vibration, and so this oscillation frequency is something that is measured and usually tabulated in terms of wave numbers. So omega naught divided by 2 pi c naught, where this is the speed of light, is what usually gets measured and tabulated. And we can take our definition here for omega naught, plug it in there, and then we can rearrange that to get a force constant based on the measured wave number and using the reduced mass here. So let's take a look at the force constants that we get for different molecules that we measure in spectroscopy. So again, that's our expression here for the force constant. Here are different diatomic molecules. Here's the measured wave numbers that we get. Here's the reduced masses, and here's what's calculated for the force constant. So this is really interesting because you can see that the bigger force constants are the ones associated with the strongest bonds, so as you might expect. So the triple bond between it and N2 has got the largest force constants of this bunch here. And you see that the carbon monoxide is also quite high. The double bonds, not as high as the triple bonds, but they have pretty high force constants. And then the covalent bonds up here the covalent single bonds are lower than the double bonds. And then you see the weakest guys here are the metal bonds, the sodium-sodium metal bond. And then above that are the ionic bonds, say between sodium chloride or potassium and chloride. So all of that sort of makes sense then. If you measure for these diatomics their vibration frequencies, then you can calculate force constants, and it's all consistent with our picture of the bonding strengths for these type of systems. Okay, so in the next video, I'm going to look at this web app by Paul Fostad when he looks at coupled oscillators, and we're going to sort of work our way towards sort of having a qualitative understanding of polyatomic molecule vibrations. And then in the last thing, I'll have you look at a vibration of polyatomic molecules video, and if you want, you can also look at this extra video, which sort of reviews some of the more fundamental aspects of simple harmonic motion.